And Assalamu alaikum. This is your Thermodynamics 2 class. So, and today is your lecture number 10. Okay, so previously I changed it to the timing to 1:30, but after this I realized that for Friday class, the time of the class is unchanged. Okay, so it will remain on 2 p.m. Throughout the Ramzan also. Okay, so can anyone confirm that what's there on my screen right now?
So we are seeing the introduction slide, lecture 10, chapter 9, gas power cycles.
Okay, thank you so much. Okay, so starting from again, your chapter number 9, gas power cycle. So previously we already talked about how to develop the different equations which are related to your uh, Otto cycle. Okay, and we already talk about the ideal conditions. Okay, so we talk about isentropic processes which are developed based on some assumptions. However, when we are talking about the Otto cycle and your spark ignition engine in the actual one, so these are not an isentropic processes because there will be definitely increasing entropy as well. Okay, so the important thing is that your expansion process and your compression process, previously when we talk about Otto cycle and there will be ideal condition, your Q is equal to 0 and it will be an adiabatic process. However, in the actual cycle, it is not adiabatic. It is there will be some heat transfer. Okay, so either that transfer towards the air, okay, or either there will be some heat addition. So we will see over there. And in order to represent that non-adiabatic process for your real cycle, so we have to use the term specifically polytropic process. Okay, so we will see that what this process is. Okay, so this called the polytropic process in which your entropy is not equal to 0, and this also come from your chapter number 4. Okay, so I hope you all have the understanding about the polytropic process. So previously when we talk about isentropic expansion or isentropic compression, we say that PV is power K, which is your specific heat ratio, is equal to constant. So this is the relation which is valid for your isentropic process. But here the important thing is when we are dealing with the actual cycle, so we have to represent the process by using this equation, which is PV n is equal to constant. Okay, because not all the processes are basic type, that is the ISO, or it can be approximate by one of the basic processes type and depends upon the polytropic exponent and polytropic index. So here previously we used the value of K for the isentropic process, but now we have to replace it with the polytropic exponent, that is the n, or it is also defined as the polytropic index. Okay, so what this polytropic exponent and polytropic index is, so the value of this will decide what process for your two state is in between your two states. So for example, if n is equal to 0, if you can just put n over there 0, so you will find out it will be turned into isobaric process. So mean pressure is equal to constant. If it is infinity, your n value, it turns out to be a constant volume process. If n is equal to k, which is our previous isentropic process, which we already talked about in the previous lecture. So if your value of n is equal to k, it turns out to be isentropic process, which is similar to the previous one, and it is an adiabatic isentropic process. It means your q is equal to 0 over there. If n is equal to 1, it turns out to be isothermal process. So these are some values which we have to decide for the n values. So which process is there for your polytropic process. So now in order to define the work, because definitely if polytropic process is happening for your expansion process, so there will be a work involved over there. So to find the work, which is called WB, is the boundary work. So it can be in between any state point, either it will be 1, 2. So if there will be expansion process or compression process between 1 to 2, so you can define your boundary work in form of M. M is your mass fraction of the working fluid, that is the air. R is the gas constant. which working fluid you have to use. T2 is your final temperature, T1 is your initial temperature, and 1 minus n is your polytropic exponent. And this n value is given to you in your problem statement. So if it is mentioned in your problem statement that polytropic exponent is the number of polytropic exponent n is equal to 1.2, for example, or it is also mentioned that polytropic index is n is equal to 1.2, so it's mean your value of n is given in your question. Okay, so now question is where this derivation come from, and so this derivation come from your chapter number 4, so we will see where you have to find it. Okay, so this is your chapter number 4, and this is page number 171, and here it is mentioned over there polytropic process. So here the derivation is there, so you have to go through it by yourself. So this is the derivation for your first, which is WB mr T2 minus T1 1 minus n, and the condition is that n is not equal to 1. Okay, because it is 1, then it will be turned into 0, and then your equation will be something else. For the special case n is equal to 1, it turns out to be this one. Okay, so this derivation you have to do it by yourself, so you have to revise it, chapter number 4, 171 page. So we will use directly these relation for to solve some problems related to polytropic process. Okay, so now coming towards again the slides. Okay, so here is the problem which is related to your polytropic process. Okay, so if you can just read it, the compression ratio of an air standard Otto cycle is 9.5. So here the compression ratio, which is your ratio of maximum pressure to maximum volume over minimum volume, is given in your question. So prior to the isentropic compression process, the air is 100 kilopascal and 35 degrees Celsius and 600 centimeter cube. So in the question it is mentioned that your compression process taken place isentropically. So it is an isentropic compression process, and the air is at, that's mean your temperature at the start of your compression process, pressure is 100 kilopascal, temperature is 35 degrees Celsius, and volume is also given over there, 600 centimeter cube, which is your V1. Now it says the temperature at the end of polytropic expansion process. So here it is mentioned that your expansion process do not taken place isentropically, but it is a polytropic expansion process. It means you do not need to use the value of K over there. Okay, so we will see what process we have to follow it, and it is 800 Kelvin, which is your T3, because your expansion process ends at point number 3 if you correlate with your TS diagram, and the value of N is 1.35 over there. So using specific heat value at room temperature, so you have to use the constant specific heat procedure in order to solve this problem to determine the highest temperature and pressure in the cycle. So highest pressure and temperature is at point number 3. Okay, so this I think I just say that T3, it is T4, 800 Kelvin, because your expansion process end at point number 4 if you just correlate with your TS diagram. The amount of heat transfer in kilojoule. Okay, so this you have to find the Q, which is your heat transfer over there, the thermal efficiency, and the mean effective pressure. So this is your question. So we will see that what is the solution of this one. Okay, so we have to start with the PV diagram. So we will try to draw the PV diagram first. Okay, so there will be a compression process between 1 to 2. Then there will be a constant volume heat addition process towards 3. Then there will be an expansion process over there. okay, towards 4, and then there will be a constant volume heat rejection process over there. So this is QR, this is your Q in. Okay, so this is your isentropic compression process, which is already mentioned in your question. And previously this 3 to 4 is your isentropic expansion, but in this question it is polytropic expansion process. So you just have to write it down whenever there will be a problem, and the line will be like this 3 and 4, and you just have to mention this is a polytropic expansion process. But another important thing is that whenever there will be a polytropic expansion process, it's mean that the heat component is added in this 3 to 4. Previously uh, W, we already talked about that there will be expansion process, there will be W, but here it is W plus Q. Okay, so there will be a work as well involved as well, and there will be a heat transfer as well, because this is not an adiabatic process, which is a polytropic process. This is the main difference between the polytropic and isentropic. So now starting to solve this question, so we will have to start from the process 1 to 2. So for process state 1, the temperature is given and the compression ratio is given. So you already know that for your isentropic process, the relation that is valid, which we already talked about in your previous lecture as well, T2 over T1 is equal to V1 over V2 K minus 1. Okay, so this is 1 to 2 is isentropic compression. So we have to use the value of K over there rather than N. Okay, so you have to use only N value when there will be a polytropic process. Okay, so this V1 over V2 is the compression ratio. So, and T1 is known to you, so you can easily find the value of temperature, because we have to find all the states temperature and pressures. 308, and it will be 9.5, which is your compression ratio, and 1.4 minus 1, and you can just solve it and you will get the value of 757.9 Kelvin. Okay, so this is your T2. Okay, so now coming towards, because we have to find the pressure as well. So P1 is known to us. P2 we can easily find by using the relation PV is equal to T. PV divided by T is equal to constant. And for two processes, for two state point, we will say that P2 V2 over T2 is equal to P1 V1 over T1. And by using this relation, you can easily find the pressure at state point 2, V1 over V2, T2 over T1, and P1. So this is your compression ratio. So this is mentioned in your question. This T2 you just have find by using this step. T1 is mentioned in your question. P1 is also mentioned in your question as well. So P2 is equal to 9.5, 757.9, 308 Kelvin, which is your T1, and 100 kilopascal of your P1. So you will get the pressure at 2238, 2338 kilopascal. Okay, so this is your P2 value. So now moving towards process polytropic process. So we will see how to find the variables for the polytropic process. So first you have to note it down, then I will move forward. Okay, so starting from process 3 to 4 now, okay, which is your polytropic process. So for polytropic process, we already know we have to find the work first, okay, because we need to find Q34 as well in order to find the total heat, which is your part number B. So for total heat addition, so it will be the combination of the heat, which is Q in 3 to 2 and Q in between 3 to 4. Okay, so in order to find that, we have to find work first. So W, so we will see that what is the W34, which we already talked about, that whenever there will be a polytropic process, the boundary work is defined as MR, your final state T4, the initial state between where the polytropic process is taking place, is 1 minus n. So n is your polytropic exponent. Okay, so in this equation, you have to find first m, because m is not known to you. R value is for air, it is a constant, you can find easily from table A2, or either you can remember it, its value is 0.287 T4. And okay, so now here what we have is T4 is mentioned in your question, because it is mentioned there that at the end of polytropic expansion process your temperature is 800 Kelvin. So this comes from your problem statement. So T3 we have to find out because it is unknown to us, and N is also mentioned in your question. So first we will start with finding the M. Okay, so for M you already know that the relation is P1 V1 RT1. Okay, so MRT is equal to PV. So from here you can easily find the mass fraction of your working fluid. So this is P1 is given in your question, 100 kilopascal. Volume 1 is also given in your question, which is 600 centimeter cube, I think. So you can just convert it into the meter cube and you will get 0.000006. And R value you can easily find out from table A2, and temperature 1 is also mentioned in your question. So from by just solving it, you will get the term as 6.788 10 raised to power minus 4 kg. So this is your m value over there. So now coming towards the point temperature at point number 3. So T3 over T4. So again it is the polytropic process. So the relation that is valid is V4 over V3, but previously we used K minus 1 when there will be isentropic process. So here we have to use N minus 1 because it is the polytropic process over there. So from here, if you can notice over there that V4 over V3 is equal to compression ratio, okay, because V4 is equal to V1 and V3 is equal to V2, and the maximum ratio volume over minimum volume is equal to compression ratio. So from there you can easily say that T3 is equal to T4 R n minus 1. Okay, so T4 value is known to you from by the question and problem statement. So it is 800 Kelvin. R value is also mentioned in your question, which is 9.5. N value is also there. So you can just say 1.35 minus 1 is equal to 0.35, and you can just solve it and you will get 1759 Kelvin of temperature at point number 3. Okay, and which is also your part number A to find the temperature with maximum temperature. So maximum temperature is at point number 3. Okay, so you have to note it down and we will move forward. And this problem is problem 9-38 from your book. Okay, so you have to correlate with your problem statement from the book as well. Okay, so now coming towards your boundary work, which is your W34. So now M is known to us 6.788 10 raised to power minus 4 kg, and now R value, which you can easily find from the table as well, and your temperature, which is 800 Kelvin at T4, and T3 temperature we just find and 1759 Kelvin, and in the denominator it will be 1 minus n, which is 1 minus 1.35 polytropic exponent, and by just solving it you will get W34, which is your boundary work for the polytropic process, is 0.5338 kilojoule. Okay, so this is your W34. Okay, so now we have to find the Q, which is associated with your polytropic process. So this is your polytropic process, and here we have to also find the Q. Okay, so in order to find the Q, what we have to do is we have to apply the energy balance equation between the process 3 and 4. So energy in, energy out is equal to change in energy. Okay, and if you can just notice over there, your Q34 is over there, then there will be one work W34, and then it is equal to, whenever there will be a polytropic process, okay, so it will be MCV T4 minus T3. Okay, so it is a similar state equation which we already talked about in the previous lecture as well. Okay, so now here you can easily find the Q34 because W34 we have just find out. M is known to us, 6.788 into 10 raised by 4. Specific heat at constant volume, either you can remember it or either you can go to table A2 and you can find this value. Okay, so now here T4 is okay, T4 is known to us and T3 is also known to us. Okay, so all the values are known to us, so you can easily find Q34. So we can just put the values over there, 6.788 into 10 raised to the minus 4. This is 0.718. T4 is 800 and 1759 T3. And plus you have to just add W34, 0.5338. So by just solving this, you will get the value 0.0664 kilojoule. So this means that this amount of energy of heat is added to the air during the expansion process. So this is your Q34. Okay, so we get this value, so we can easily find the Q in as well. Okay, so in the next step we will try to find the Q in. So you can note it down, then we will move towards the next step. Okay, so you first you have to also find the P3 as well. Okay, so we already find the temperature at 3, so you can do this process also. So P3 V3 over T3, because this equation is valid for any process over there. So T2. Okay, so you already noticed that this will be cancelled because V3 is equal to V2, and you can easily find the pressure at 3, which is T3, which is 1759, T2 757.9, and your pressure at 2 we already find in the part A, so 2338 kilopascal. So you can just solve it and you will get the pressure value 5426 kilopascal. Okay, so this is your part A, which we have to find the pressure and temperature at point number 3, which is your maximum pressure. Okay, so now coming towards the Q in, because in your part B you have to find the total heat transfer. So in order to do this, so this is Q in is equal to Q23, so here, and plus Q34. So this is the addition of these two heat transfer over there. So Q34 we already find for the polytropic process over there, and Q23 we can easily find. So Q23 is equal to, because it is a constant volume heat addition process, and the relation that is valid over there is MCV T3 minus T2. Okay, so M is known to us, CV value we can easily find, T3 and T2 also known to us. So you can just plug in all the value and you can easily find Q23. So 6.788 into 10 raised to power minus 4. CV value is 0.718. T3 value is 1759 and T2 value is 757.9. So you can just solve it and you will get the value of Q23 0.487 kilojoule. Okay, so this is your value of Q23, and from there you can easily find the total heat transfer, which is Q in. So you can note it down, then we will move forward. Okay, so Q in is equal to 0.4879, which is your Q23, plus 0.0664, which we already find, which is your heat which is associated with this process over there. So you can just add these two values and you will get 0.5543 kilojoule of your total heat. Okay, so now coming towards the part number C, which is to find out the efficiency. So we already know your efficiency is equal to W net over Q in. Okay, so in order to find the W net, so W net is equal to Q in minus Q out. So Q in we already know about it, so this is the value of Q in. Q out we can easily find out by using the relation, which is Q out is equal to M, because it is a constant volume heat rejection process, temperature at 4 and temperature at 1. So this relation comes from your, you can just go to slide number 1 of the chapter number 9, you can easily find this relation. Okay, so by just plug in all the value, you will get the value of Q out as well. So 6.788 into 10 raised to power minus 4. CV value is 0.718. T4 is given in your question, that end of the polytropic expansion process. The temperature is 800, and at the start of the compression process, the temperature is 308, is also mentioned in your problem statement. So from there you can get 0.2398 kilojoule of Q out. So from here you can easily find your W net. The W net is equal to 0.55543 minus 0.2398, and that turns out to be 0.314 kilojoule. Okay, so this is your W net. So if W net is known to us, we can easily find the efficiency of our cycle. Okay, so your efficiency is equal to 0.3145, which is your W net, and Q in is equal to 0.5543, and if you can just calculate it, 56.7%. And here keep it, remember that the equation which we already derived is 1 minus 1 over R K minus 1 is not valid for the polytropic process, because this equation is developed for the isentropic process by you doing the assumption of isentropic processes. So that's why I do not use this equation. So you have to use W net over Q in, by which we have to apply the method for polytropic process. If it is mentioned in your question, if there will be expansion process is polytropic, so you have to apply that principle of polytropic exponent for 3 to 4. If it is mentioned it is a polytropic compression process, then you have to apply the same principle for process 1 to 2. Okay, so now coming towards your part number D. So part number D is to find the mean effective pressure. So mean effective pressure from the previous problems as well, we know that it is the W net, and in the denominator it will be V1 1 minus 1 over R. So previously we used the specific volume, so now here we use the V1 because here we are using W net over there. Okay, and previous question we used W dot net, which is your kilojoule per kg, and then we use the specific volume over there. But in this problem we are going to use W net, which is in kilojoule, so we can use directly volume for this problem. So W net is equal to 0.3145, and V1 value is mentioned in your problem that the volume at your initial state is V1 is 600 centimeter cube, so you can just convert it into meter cube, and the compression ratio is also mentioned in your question, and you can just solve it and you will get the value of your mean effective pressure as 586 kilopascal. Okay, so this is the solution whenever there will be a processes involved is the polytropic. Okay, so if you have any question you can ask me. And also by just assuming this process to be polytropic, you will get more closer value to your actual cycle, and so that's why most of the time it is recommended to use the polytropic processes to find the efficiency, accurate efficiency for your cycle as well. Okay, so I hope there will be no question. It is an easy questions, and there will be nothing difficult over there. So here is the one question which you have to solve. So it is a again easy question and similar question to the previous which I already solved over there. So it is the Otto cycle. Compression ratio is mentioned over there. T1, V1 is mentioned over there. Only the values are changed, and you cannot find this question at end of your book. You have to do it by yourself. At the end of the polytropic expansion process, 900 Kelvin, so it is mentioned that the polytropic expansion process is involved over there, and the compression process is isentropic, and the polytropic exponent value is 1.2. So using the specific heat value at room temperature, so it means you have to use constant specific heat values, and the highest temperature and pressure in the cycle mean T3 and P3, you have to find the amount of heat transfer in kilojoule, thermal efficiency, and the mean effective pressure. So this is your question, and again for this you will get 0.2 absolute mark for all the students who will send their work neatly and present it in a correct way. So all the things over there. So if you have any question you can just inbox me, and there will be no time limit to solve this question. You can send it to me by night as well. Okay, so you just note it down the question, so then it will be disappear, so there will be no difficulty for